more time, that would be accepted with no late penalty. Okay. I will hand out lab 2 after the exam, soon after the exam, so that you can look at it and think about it. But you can take a little extra time for lab 1 if you need it. Okay. Exam is in this room, not during the class lecture time. It's an evening exam, as I mentioned. So keep that in mind. Okay, it's closed book, closed notes. I will have some extra office hours next week. If you want to stop by, discuss any part of the material that's not clear, and send out a note about that, so you can come by and talk to me, okay, on Monday or Tuesday. Yeah. Okay, so lecture, so what is on the test? I mentioned that briefly in my email. Lectures 1 through 13, which is what I will do on Wednesday. Okay, so everything from the beginning through this Wednesday is on the test. Next week, whatever I do is not on the test, it's only for the final. Okay. Any other questions? So let's get started then. So just a quick recap from last time. We were talking about this problem of naming. Naming is an issue where you or an application provides the name of an object or resource, and the naming system will then map it to the object that it is referring to. And specifically, if our interest was, if you have very large distributed system and there are lots of entities, then how do you design a naming system? And the main takeaway from last class was, as the systems get larger, the naming system itself becomes distributed, and typically you organize the names in some hierarchical fashion, and looked at DNS as an example of that. Okay, we did not get to LDAP, so I'm going to finish that, and then we'll switch gears and talk about a new topic later today. Okay. So this is just a slide that was left over from last time. I was talking about DNS, if you remember, and I showed you examples of actual DNS records from local machines at UMass and whatnot. This is a similar example that is actually directly taken from a textbook, where it shows you different kinds of records. So I talked about NS record says name server, those are the DNS server for that domain. MX records stand for mail servers. There may be more than one, so you see multiple mail servers that are handling email for that subdomain. A record is a basic kind of record which simply takes a name and then maps it to an IP address. And that's the most basic kind of record. There's a CNAME record, which is an alias record that simply says this name is an alias for some other name, and there will then be an A record for that other name somewhere. Okay. The A record for this machine is actually here. Okay. So that's an alias record, and then you will see various other kinds of records, which info records that are just comments and so on. Okay. So that's simply an example of DNS. As I said, it's a distributed database of records which have keys are the names and the values are the whatever information that record is storing for it. Okay. So that's where we had left it last time. So what I'm going to talk now is a more general naming service called X.500. In the naming service are also referred to as directory services. And what these directory services do is they generalize the kinds of functions that DNS provides. Okay? The DNS essentially supports only exactly one type of query, where you specify a name and it finds you the record corresponding to that name. Okay? That's all you can do. You have to give a full name of a machine, and then it tells you whatever record is present for the name. Okay? Now there may be directories, you may need a directory service that requires you to do other kinds of queries. Okay? An example may be, let's say you run your telephone directory, okay, the telephone book, you put it online, okay, yellow pages are put online. Now you can think about what are the common kinds of queries you can make on a telephone. You can do the same kind of lookup you do in DNS, where you specify a name of a person and you look up their phone number. Okay, that's the analogous query in the DNS world. But if you think about Yellow Pages, there are many other kinds of queries you can perform. You can say, show me all the listings for a plumber. Okay? In this case, you do not know the name of the person. Okay? You simply know some attribute, and you are basically looking for all matches that are going to show up that have that attribute. Okay? So you have other kinds of queries where you can look up entities based on attributes instead of their full name, and you want to find all sorts of matches. DNS doesn't support that kind of queries, but X.500 does. So X.500 is a more general directory service. It can be used to perform more general lookups, as well as it can be used as naming services in a broad variety of domains. Okay, so that's X.500, but we won't talk about X.500. We'll talk about a simplified variant of X.500 called LDAP, which is Lightweight Directory Access Protocol. Okay, LDAP is widely used. Okay? It is actually a simplified version of X.500, which has a lot more complexity than you need for most directory services or naming applications. Okay? Now, if you go to the UMass webpage and look at the people finder, okay, that's running on an LDAP server. Okay, there you can specify the last name of a person, you can specify the first name of a person, you can specify arbitrary attributes, and it's going to show you all the matches for that attribute. Okay, so that's an example of doing more general queries. Okay, now LDAP can be used for a variety of other things, not just to keep people records. It is used for username, passwords. When you log into a system and you specify your username and password, you do a lookup saying, is this password corresponding to that user? So those kinds of records are also stored in LDAP services, as well as lots of other things like what resources are present and so on, like printers in a domain. So it is used for a variety of different scenarios. So practically every commercial operating system today supports a directory service, which is some form of LDAP. Okay, so here are some examples, but let's take a question. Yes.
So what's the difference between the query to the database and RDP? It seems to me it's similar and you look for the attributes. So it's look for the attribute in the database, right?
So you're asking what's the difference between a database and the LDAP? Okay. So LDAP is a service that can be built on top of a database. Okay. LDAPs will specify some schemas for you. It will specify how records are stored. It may specify encryption. You may not want to store passwords without encrypting them and so on. So there is a layer that you, a database is a very general thing. It can be used for anything. Okay, so you can think of LDAP as a directory service that is built on top of any kind of a database, but it specifies schemas. As we'll see, the schema is defined and what kind of queries can be performed are defined and so on. Okay? Of course, if you give yourself a database, you can build a directory service on top. But then you will have to define all sorts of things that LDAP will do for you. Okay. So here is an example of several directory services that are out there. Windows world, you basically have something called Active Directory, which is its directory service. That's where username, passwords, resources in the system, all of those are stored. So that's also an implementation of LDAP. In the Unix world, you have something called Open LDAP. If you have Linux, and you need a LDAP service, you will often use Open LDAP. Mac OS X also uses a variant of Open LDAP for the directory. So most of the operating systems, commercial operating systems, will use some form of directory services to keep track of all sorts of resources, just starting from user account, but many other things as well. I'm going to show you some examples here. So here is the schema that LDAP may define to store people records or machine records. Okay, so in this case, you basically have a schema where you have to define a country, which is a C, a location, an organization, which is an OU, a common name, and then you can specify attributes. So you can basically use LDAP also to keep track of local machines, not just DNS, but LDAP can be used to say, here's a mail server, here's a print server, this is its IP address, here's a web server, and so on. So that's just one example. Okay, so you're using LDAP similar to using DNS, except that here you can make more general queries that you would not be able to do in case of DNS. DNS, you can only do one kind of query, which is really specify a machine name, get an IP address. Here you can ask arbitrary query next time, show me all FTP servers in the department. You can say, show me all machines that have a certain prefix. Okay, you can do all sorts of wildcard queries that you will not be able to do in a more specific case of DNS. Okay, so the way LDAP works is it keeps its namespace in a hierarchical fashion, very similar to DNS. So you will see that the country level node is at the top, and then there's an organization, and that's an O record, and there's an organizational unit, which is really a department. There's an OU record, there's a CN record, which is the name of the server. There are host names at the end. Okay? So this is the namespace that LDAP will define, and you can have people as well. So these are the machine. This may be the machine subtree. Okay? There may be a people subtree here, which is all the people in that department with their names and office room numbers and phone numbers and all of that kind of stuff, and email addresses. Same kind of stuff you'll see in People Finder. People Finder is an LDAP directory where, I guess that part of the subtree is not shown, but it's only keeping track of the people side of the subtree, not the other one. Yeah, so you can have many different LDAP servers. Some may be managing machine records, some may be managing people records, some may be managing other resources that you have in the organization and so on. Okay. So this is something to keep in mind. You probably encounter LDAP whenever you log into any Unix machine. Okay, so if you just type your username, password, it's actually trying to authenticate you against some sort of an LDAP service. It may be Active Directory in Windows, it may be Open LDAP in Unix and Macs and so on. Any questions here? Okay. So I'm going to switch gears a little bit. Okay, so that's the end of the discussion on naming. Keep in mind that was an entire chapter from the book. It's a shorter chapter. So we essentially only spent a lecture on the whole chapter. So you have to make sure you keep up with the readings because we are covering material at a fair clip. Okay, so we are done with the naming chapter, and then we are going to move on to the next chapter of the book, which I'm going to introduce in a moment. Yes, your question there.
Is there any disadvantage of using LDAP because it is so good in that
Okay, good question. The question is there any disadvantage to using LDAP? Why do we use it? Why do we use DNS? So I would say they are each good for their own thing. Okay, DNS is a specific directory service that's designed only for doing machine IP, names to IP address translation. There's a lot of services that just do that, and it does it well. Okay? And for that purpose, it serves its purpose. Now, if you have any other kinds of needs, it won't serve it, and in that case, you should use LDAP. Okay? So, if you think about the web, there will be lots of browsers that are going to lots of web servers. All of those require a DNS lookup, and it does its job very efficiently. It's out there, it's been deployed for decades, and that's good enough for what it's trying to do. There's no need to overcomplicate DNS for use cases that are not very common. Within an organization, you have to do other kinds of things. But DNS is not designed to track people, but within an organization, you have to track people, user accounts, their email addresses, their phone numbers, their passwords, their machine names. So for that, DNS doesn't work. That's not what it was designed for. So you have something like this. So you have different directory services that are designed for different needs. That's all I was trying to point out. Not that one is better than the other. They're each designed for what they do. Any other questions here? Okay, so we are now going to, as I said, switch gears and talk about a different topic. This is going to take a good third of our class. Okay, this is sort of the core of what you will see in distributed systems, and I'm going to label this entire topic as canonical problems in distributed systems. So we'll look at a set of problems that are going to arise over and over again whenever you try to design any sort of distributed system. We are going to study each of this problem in the abstract, but you will see example scenarios where when you try to build any distributed system or distributed application, you encounter them over and over again, and this is not even the entire listing, this is just the first few problems we are going to talk about. Okay? And these problems, so we will basically use this as a foundation to build any distributed system. So we'll start with things like clock synchronization, okay, that I'm going to cover today. Then we'll do leader election. Then we're going to do distributed mutual exclusion or distributed locking. We'll talk about distributed transactions. We'll talk about consensus and agreement, and that's the context of looking at things like faxes. Okay, so these are all very common problems that you will have to look at. So we are going to just lump them into this category of canonical problem. And we want to look at very specifically how specific systems look at them. So we look at them in a little more abstract or a more general way. So today we are going to talk about time ordering and clock synchronization. That will be the first of these topics. In each class we are going to actually look at one of these topics. So it will take several lectures to finish this. So that's going to be our core of what I would consider is distributed systems concepts. Okay, so let's talk about clocks and clock synchronization. Okay, so first I'm going to introduce what is the problem that we are going to look at. Okay, so first thing you need to keep in mind is every computing system has a clock of its own. Okay, that's a chip that is actually keeping time on that machine. Okay, and you can look at the machine and it will tell you the time. And you can use this time for a variety of purposes. So this is going to be called a system clock on the machine. Okay, and any entity is going to use that. So if you create a file, it's going to be timestamped with the creation time and so on and so forth. Okay. Now if you have a centralized system, you basically use the clock on that machine to basically timestamp events, timestamp files, do whatever you need to do to reason about time. And that is not going to be a problem because even though that clock may not actually correspond to real time, you're just using that as your authority to figure out what's the time on that machine. Now the problem arises when you have a distributed system of many machines. Right? In this case, each machine is going to have its own clock. Every machine will have a clock which will tell you what time it is. And you will see problems if the clocks are not synchronized, and often unless you do something specific, your clocks are not all going to be identical. A clock on one machine may be off from the clock on another machine because this clock may be ticking faster than the other clock. Just as a normal clock, if you have two clocks in your house, after a while you will see that they are going to drift from one another. Unless you synchronize them, nothing will prevent them from, nothing will force them to tell the same time. Okay? So now if you have a distributed system and now you are trying to solve some problem that depends on clocks, you are going to often have issues because the clocks are not synchronized. And I'm going to show you a very simple example of an issue. Okay, so here is an example where we are going to use timestamps that are assigned to files to reason about something, and a distributed system, you see, that will quickly get us into trouble. Okay. So here is the problem that we are going to look at. So let's say you are actually trying to compile some project file that you have. Okay, let's say it's a C file, you compile it. Okay, so you are going to use the tool, let's say make. I presume you all know what make is. Okay. So you run make, and the way make works is it's going to look at the source file, look at the object file if you previously compiled it, it compares the timestamp, and if it sees that the source file is newer than the object file, it assumes the source has changed, or somebody has made changes to the source code, and it will recompile the file. That's how make works. Yeah, any build tool that you may have encountered, and there are like tons of them, they all work on the same basic principle. They are going to see what files changed, and they do that by looking at timestamp, and they only recompile the files that have changed, not everything in your project. You may have lots of files, but if you only change one file and run make, it only recompiles that one file. So now let's assume that you compile the file, right? And then you went back and you are looking at the source code and you make some new change to that file. Okay, so you change the source code and you hit save. Okay, very straightforward. You compiled your project, and you went back to your source code, you basically made some change and you hit save. Okay. Now if it so happens that your build machine is different from your desktop where you are editing the file, the clocks won't be identical. If you are using one machine for development where you are building the project and writing code, this is not an issue. Okay, but I am simply pointing to a scenario where you have a separate build machine and your machine where you write the code. This is often true in any software development environment where you have a set of build servers that are fast machines that can compile very quickly. Okay, your desktop doesn't need to be very powerful, you are just writing code, but when you are building code, if you have a large project, you need faster machine. Your build machine may be different. Okay, that's a scenario. So now if the build machines, if your machine's clock is behind the build machine's clock, okay, your clock is slower, you modified the code, you saved it. Yeah, it's going to get a timestamp of whatever clock is, whatever the current time is on your machine. And say recompile, the build machine is actually running ahead. The previous compilation file, the object file may still have a newer timestamp than your source code, okay, because the two clocks are offset. So the make in this case will not see that the file has changed because it's simply looking at timestamps, and the timestamps, the source code file still has an older timestamp than the object code because your clock is maybe 10 minutes behind or something like that. Okay, and you will not be able to compile the file. And you will see problems. So if you have these kinds of problems, you will essentially get into trouble. So because what you are doing is you are reasoning about timestamps on two different machines. Okay? The timestamp on the object file was assigned on the build machine, okay, different clock. The timestamp on the source code was assigned by your machine when you saved the file after changing. That's a different clock. They are not synchronized. They're off by one another. Okay? And if you compare them, they are actually meaningless to compare. They are not synchronized. It doesn't tell you anything. Yet you are trying to see which is newer. Doesn't make sense. Is that clear? Okay, so what would we do to address this problem? Yes. Okay, we have version number, so that we will come to later. Since you are talking about clocks, we will come to version numbers in a little while. Okay. You can of course look at the version number. C code will not do that, but you are right. I'm going to wait on that for just a minute. What other simple solution can you think of?
We compile everything.
Okay, you can recompile everything. That will defeat the purpose of make. But yes, you can say I can't depend on clocks, I'm going to recompile. Okay, so you can figure out that the clocks are off and try to adjust them. Okay, so why not synchronize the clocks every so often so that the clocks are similar, they're not drifting apart. Okay? This is how most computing systems actually work. Yeah, they are not going to sit and figure out two machines. What they will do is they will actually try to ensure that clocks on different machines are actually, if they drift, they will be resynchronized periodically. Meaning that you will actually look at the clock values and try to set them to the same value. Exactly what you would do if you see two clocks in your house that are drifting, you'll go and reset the clocks to what the actual time is. The same thing you'll do in a computing system. Every so often you go and reset the clocks so that they'll all stay at the same time, and then they start drifting again, and you keep repeating this. Okay, you keep resetting them. That's called clock synchronization, okay, which I'm going to come and talk about in a slide or two. Okay, but before we do that, I'm going to first define what a clock is and how clocks work, so that way we have some idea of what clock synchronization means. Okay. So there are different kinds of clocks you can get. Okay, so the computing clocks are typically crystal-based clocks. Okay, so you may have seen wristwatches that are quartz-based. Quartz is a crystal. Okay. It oscillates a certain number of times every second. But the way the clock is telling time is actually counting how many times this crystal is oscillating. And if its oscillation frequency is X, every time it oscillates X, the clock ticks by 1. Okay, so you're simply using the oscillation of a crystal to determine how to tell time. Every time it ticks by, it oscillates by a certain value, you're going to tick by 1. Okay, now, but those are not the most accurate clocks. Those are going to have inaccuracies because the oscillation frequency depends on environmental condition. If the temperature is warmer or cooler, then it may oscillate at a slightly different frequency from its natural frequency. And this is where you're going to get drift. Okay. So essentially computing clocks which are crystal based, they're accurate to 1 part in a million, which essentially means that every time million seconds you're going to be off by approximately a second. It's going to drift by that much time. Okay. And of course temperature changes, environmental changes, humidity, all of them may make them drift faster. The most accurate clocks you can find today are called atomic clocks. Okay, so atomic clocks essentially look at properties of an atom to tell time, in terms of how many times electrons may circle around the atom and so on. Those are the most accurate clocks we have today. Okay? So for our purposes, the most accurate clock, the real time, okay, something has to be in the real time. The real time is an atomic clock somewhere. Okay, there are a few, every country runs its own atomic clock to say this is the actual time. Okay, and every clock has to basically reference itself with respect to that atomic clock. So if you've heard, in the US, there is a site in Colorado where there are atomic clocks, and that is basically keeping time for the rest of the country. Okay. Similarly, there are many such sites. You have something, if you've heard of Greenwich Mean Time, which is now called UTC, there is an atomic clock in UK which is telling time for the UK. That's in Greenwich, UK. And so, okay, so from our purposes, okay, because if every clock is inaccurate, you don't know which clock is the real time. You need something to be a reference. The atomic clock is a reference. That is basically what every other clock needs to synchronize to, because that's the most accurate clock we have in the world. All other clocks are less accurate, so let's have the less accurate clock synchronize with the most accurate. Okay, that's basically how we are going to tell time. Okay. Now just contrast that to the old way of telling time. So how did, before atomic clocks and crystal clocks were invented, how did people tell time? Yes. So you use sun to tell time. Okay, the whole notion of time comes from sun. Noon is the time and the sun is directly above, there are no shadows. Okay, that's basically the old way of telling time. So you use astronomical metrics, used to use astronomical metrics to tell time. Okay, now, as it turns out, atomic clocks are even more accurate. So this depends on how quickly the Earth is rotating. 24 hours is basically what our clock is based on. We assume that the Earth revolves around its axis in a 24-hour cycle. Okay. But as it turns out, atomic clocks are even more accurate than how quickly the Earth is rotating. The error with Earth is actually slowing down very slowly. So the days are getting longer, but ever so slowly. And atomic clocks are even more accurate than that. So it's just why we use atomic clock rather than property of the sun to tell time. Otherwise, you could have just used that to say that's our most accurate clock. Okay, so today's clocks are more accurate than anything that we have used in the past. So that is our notion of global clock, not a global clock, sorry, a reference clock. So that is also called coordinated universal time, where there is a body that coordinates how time is determined based on atomic clocks that are maintained around the world. Every so often you're going to add a leap second to the year. I don't know if you've heard of a leap second, you must have heard of a leap year. A leap second essentially says because the Earth is slowing down, every so often you have to actually artificially add a second to make the year 1 second longer, so that noon is still where it is. Otherwise noon is going to drift. What we call noon based on atomic clock will drift based on what is actually noon. And soon you will see that there is no shadow at 11:59 instead of noon or some such thing. So you have to make this adjustment periodically. Now how do you actually coordinate with an atomic clock? Typically all these atomic clocks are going to broadcast their time over some sort of wireless frequency. If we listen onto this frequency, it will basically listen on to whatever is the actual time, and then we'll synchronize with that time. Okay, newscasts often have that beep that comes, and those are all coming from the atomic clocks. Okay, so if you have 9 o'clock news, you'll sometimes hear this beep, 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 and then the news starts. That's essentially listening onto an atomic clock. Okay. So that's the background we need before we go off and talk about synchronization. We need some reference clock, and we'll assume always we synchronize with an atomic clock. Any questions here? So now we will talk about clock synchronization, where we will assume that there is always a master machine. Yeah, the master machine is the reference machine that is going to provide the reference time for whatever other machines are trying to synchronize with it. We typically assume that the master is itself synchronized with some atomic clock somehow. How that is done, we will not worry about. You can simply buy a receiver that is listening onto an atomic clock, and your clock on the machine is simply being synchronized all the time with that receiver. You can simply buy these devices that you can just connect over USB to your machine, and somehow your machine is going to be synchronized. So we'll assume the master is synchronized with the atomic clock, and all other machines are trying to synchronize with the master. Is that problem clear? What we are trying to do? So now we are going to look at a couple of concepts, and then we'll look at our first clock synchronization problem. Okay, so we'll try to define how clocks behave on different machines. Okay. So we will assume Okay, so this figure here is showing two axes. The x-axis is real time, how time is ticking. The y-axis is how the clock is ticking. Okay? So ideally, if your clock was perfect, every time real time advances by 1 second, your clock has to advance by 1 second. Okay, then your clock is in perfect sync with real time. Okay, this is a perfectly synchronized clock. Okay? So a perfectly synchronized clock is essentially going to have a slope of 1. Okay, basically it says every time time is going to advance by second, clock is advancing by second. So we are both advancing at the same time, that y equal to x, that's the slope that we want. Okay, so that's perfect time. But in reality, your clocks are going to be faster or slower. Okay? So here is an example, this dotted line here is an example of a slower clock where every time time is advancing by a second, your clock advances by slightly less than a second. So over time it is going to slow down with respect to real time. Okay? So any clock that's actually slower is going to basically have a slope that is strictly less than 1. Okay? And then what is shown on the top is actually a faster clock where every time real time advances by 1 second, the clock is ticking by a slightly more than a second. So it's going to gain time. Okay? It's going to run faster than real time. Okay? So any real clock will actually be slower or faster than a perfect clock. Okay, we'll assume the only thing that's perfect is an atomic clock as far as we are concerned. Is that clear, what I just said? If it's not clear, then nothing in clock synchronization will start making sense. Okay, so we'll call this drift, okay, meaning that the clock is actually drifting away from real time. Okay? You can have a drift that is faster or slower than real time. So all clocks are going to drift. Okay? So essentially we will assume that depending on the type of a clock, it will have a certain drift rate rho. Drift rate rho says how inaccurate is the clock. Okay, so for a given clock there's a drift rate. Maybe you have a wristwatch that loses 5 minutes every month. That's the drift rate of your wristwatch. Other clocks may have other drift rate. Every clock is going to have a drift rate, which is essentially how much off is it with respect to a perfect clock. That's our drift rate rho. So essentially we will now bound our drift or the amount of time your clock drifts based on the drift rate, which essentially says dc by dt, essentially says how much is the clock ticking with respect to real time, is going to be bound by 1 plus rho 1 minus rho. So in real time, if you have a drift rate rho, that says that your clock is within these two bounds. Okay, if you say it's off by 5 minutes every month, that means it's off by plus minus 5 minutes. That's what this is saying. So the drift rate is capturing the plus minus, the inaccuracy in the clock. Okay. So what this says is now if you have two clocks, okay, they are going to essentially drift by, let's say both of them are drift rate rho, they are going to at most drift by 2 rho every delta time units. Okay, with delta time, I should say that, it's going to drift by 2 rho times delta t every delta t time. That's the amount by which they are deviating from one another. Each clock is drifting by rho. If you have two clocks, you want to see what is the relative speed by which they are drifting away from one another. That is bounded by this. Okay, because the worst case is one clock is slower than real time, the other clock is faster than real time. So the maximum drift you will see between those two clocks, the maximum deviation is 2 rho times delta t every delta t seconds. Okay, is that clear? Okay, so not very complicated. So what that essentially says is the clocks are drifting by at most these many seconds every delta t second. Okay, and now if you want to keep your clocks accurate to within delta seconds of one another, and that means the deviation between the two clocks should never exceed more than delta. You say that I don't want the two clocks to be off by more than 2 seconds at any point in time. If you want to guarantee that property, you have to resynchronize every delta over 2 rho second, meaning that every delta or 2 rho seconds you have to have the two clocks reset themselves, so they again are their times are the same. When they'll start drifting, then every again delta or 2 rho seconds will resynchronize them, and so on and so forth. Okay, is that clear? A very simple idea. It just says clocks are drifting away from one another and you want to limit the drift to a certain value. How frequently should you resynchronize them? Okay, if you want to limit the drift to delta, which means they shouldn't be off by more than delta from one another, and if they're going to have a max drift of rho, they'll be off by 2 rho delta t or one another, then you resynchronize them delta over 2 rho seconds. Okay, that's the frequency which we should keep resetting the clocks. Okay? So all clock synchronization algorithms are going to be based on this very simple concept. They are going to have some drift rate. Based on the drift rate, you would basically say, I would say how much inaccuracy are you willing to tolerate. Okay? The inaccuracy is delta. You say, I cannot tolerate more than a drift of whatever you specify, 1 second, 1 millisecond, you specify that. And then based on that, you say you have to now run your synchronization every so often and keep resynchronizing. Yes?
So computer may ask time to the receive next sound, and by the time it receives a response,
So you are asking a question how clock synchronization is actually done. I'm going to show you algorithms in just a moment. Okay, that will answer exactly that question. This is simply saying how frequently should you run the algorithm. It's not saying what the algorithm is. How do you synchronize? So that we are going to come to. Sorry, what's the question?
Rho is a constant, not a frequency. It says a function of time.
Okay, is rho a constant? Is it a function of time? You can pick the worst case rho. Let's say you take all sorts of, let's say you take quartz watches, as quartz being a crystal. You subject different kinds of quartz crystals to all sorts of environmental conditions and say, here's the worst case I have observed for this kind of clock. Okay? So all clocks will be less than that. So you can pick rho as your worst case for this type of clock, right? So yes, otherwise if you pick something for a specific clock, if the temperature changes or goes from winter to summer, the rho itself may change. Okay? So you pick rho based on the property of however you build the clock and try to pick some worst case value so that any clock built using that technology is going to be within rho, as an example. So that's just one way to think about it. Okay, so now having figured this out, we will try to see how to actually perform the clock synchronization. Here's the first one that we are going to look at is a very simple algorithm called a Christian's algorithm. Okay? So here we are going to synchronize all machines to what is called a time server. Okay? Time server is our master server. It's simply a machine that is itself synchronized with some atomic clock somewhere. And then what our job is, to every delta over 2 rho, we want to then go and run the resynchronization algorithm. Okay? And how do you run it? You basically, machine is going to request the time from the time server every delta or 2 rho seconds. Every so often, your machine is going to ask the time server, what's the time? Okay? The time server will tell you its time and you are supposed to resynchronize with that time. Okay? But of course, there are some subtleties when this happens. So here is a picture of what's going to happen. So this is, let's say, time is now going downwards. Okay? So here is your time server, this line. This line is your server machine. Okay? So at this point, you start the clock synchronization algorithm. You send a request to the time server saying, what's the time? That's going to be a network message that's going to propagate to the time server. Okay? It's going to take some time. Okay? Messages are not going to go instantaneously. Okay? They will take some propagation delay. So at some later point in time, that message has reached the time server. Time server will then process the message, and the message says what is the time. So at this point, the time server, the software on the time server actually asks the hardware clock saying what's the time. It picks up time t. Okay. And then it takes time t and it sends off a packet saying my current time is t, and that packet is going to reach here at this point in time. Okay. So now if you blindly take the time that has arrived from the time server and set it to the current clock, you will see that your clock is already off by at least the propagation delay. Okay, because the time that was actually sent was t. By the time that packet came here, some time has elapsed. Okay, so you cannot actually simply take the time that the time server tells you and say, I reset my time to that. That's not going to work. Okay? At the very least, you will need to estimate the propagation delay and correct for that. If you could actually look at this duration t reply and you set your time to t plus t reply, you will actually be fine. But then the question is, how do you estimate it? There's nobody telling you what the propagation delay is. You will have to estimate it as part of the clock synchronization algorithm. Okay? And all clock synchronization algorithms are going to vary just based on how they estimate the request to the time server. The time server and you do that every delta over 2 row seconds. The time server sends you back the time. Okay? But then how do you actually estimate the time to set on the clock by estimating the propagation delay is where all clock synchronization algorithms may vary. They will have different ways to estimate this delay. Christian's algorithm does something very straightforward. Okay? It makes an assumption that the delay on the forward path and the delay on the reverse path are the same. Okay? It's assuming that you are going to have the same propagation delay to send a message from machine A to B as B to A. Okay? In that case, what you are going to do is you know what time you sent off the request. You know what time the reply came back. These two things are known. You also know T. So what you will simply do is you will take these two values and you will divide it by half. And you will say that T reply is essentially T request plus T reply over 2. That's an estimate. So then you will simply take T. You will take these two values, you will divide it by half, and then you will set the time to T plus that value. And as you can see just in this picture, they are not exactly identical. It may, the network may be faster to send your packet than it's to receive packets. All sorts of things may actually go wrong. So this is simply an estimate. It's not an accurate value. Yes, so this is why no clock synchronization algorithm is going to be perfect. They are all going to make estimates of the delay. They can never be perfect. There's no way to be perfect. Yes, so they will all have an inherent inaccuracy built in. Okay? Even though the time server itself may actually know the time, because asking the time and setting your time is an inaccurate process, you will always be off. Okay? The better that estimate is, the better your clock synchronization algorithm. Some clock synchronization algorithm may run this over multiple rounds. They may ask the time 10 times. They make 10 estimate. They may take the average of those 10 and then do it that way. Okay? So there are many ways to run this. Okay? So Christian's algorithm is simply doing it once, but as is mentioned here, you can improve accuracies by using the sequence of measurements. Is that clear? This is the simplest clock synchronization algorithm. Okay, there's a master time server. You send a request asking for time, you get back a reply. You'll use the time from which you send to the time from which you receive the reply. This is known because you know when you send the packet, you timestamp that event. You know when the packet came back, you timestamp that event. You assume that the delays are identical in either direction. You basically then halve the time. And then you use that as an estimate of T reply. Okay, is that clear? Okay, so that's one algorithm. I'm going to show a different algorithm called a Berkeley algorithm, which doesn't use a time server at all. Okay? In the Berkeley algorithm, you are just synchronizing the clocks relative to one another, even though there is no master server that's telling you what the time is. So think of a collection of machines. Since you are trying to reason on events across these machines, what you really want is for the machines to be synchronized with respect to one another. Okay? But you don't really care at this point whether it's synchronized with the master time server. You just want two machines to actually have the same clock value to the extent possible. Whether the clock value actually is meaningful with respect to real time is not a concern in this case. Okay? So what Berkeley algorithm is, it's a distributed algorithm which is not going to use a time server. There is no UTC receiver. UTC receiver is simply universal time coordinates, so you don't know the exact time. So you will still have a master and slave, but the master is now no longer synchronized. You're simply trying to ensure that clocks in a group are all the same. Okay? So this is, think about it this way. Maybe you and your friend decide to meet at a coffee shop exactly at 3 o'clock. Okay? You say, let's synchronize our clocks so we both reach there at 3, and you basically ensure the two of your clocks are matched up. Whether those two clocks have any notion of what the real time is not important, because you are trying to synchronize yourself. Okay? Same thing here. Okay? Clocks are being synchronized with one another in a group. The group itself may be off with respect to real time because there's no time server, but that's not important in this algorithm. Okay? So the algorithm is very simple. The master is going to periodically poll all the slave machines for their times. is going to compute the average time in the system and is going to rebroadcast, saying here's the average time. Okay. So essential idea is that some clocks are going to be fast, some clocks are going to be slow. So we will basically take the rate at which an average clock is ticking in the system, and then you set everyone to the pace of the average clock. Okay. So the way this is done is you will ask everyone for their time, you will take the time, you will compute an average time in the system based on the reported values, and then you will tell everyone to set the time based on the average. Okay, here's a picture to show exactly that. 3 machines. Here you will see this clock is slow, okay. This clock is fast, but and the clock said the time demon is 3, time here is 250, here is 325. Okay, so you ask each machine including itself for the time. Everyone sends saying I'm 10 minutes slower, I'm 25 minutes faster, and the clock server is the same. So you will take the average of these values, and then you'll ask everyone to set their clock to 305. That's the average of these 3 values. Okay. This ensures that nobody is either running too fast or too slow. Everyone is making progress at the rate of the average clock in the system. Okay. You may not need to do that. The time server may decide I will reset everyone's time to my time. But if the time server is actually faster than everyone else, it will drag everyone to be faster. The assumption is if you average things out, you may actually have more semblance of a real time than if you just use a master that's itself not synchronized. Okay. Now, of course, you have to deal with all the issues of figuring out the propagation delays and all of that, which are ignored. That's the same as the Christian's algorithm. Okay. They're simply showing you the concept of what is being done. Okay, any questions here? Yes.
But even after the master sends them a time, the propagation delay will be different on different machines.
Yes.
So how will it be synchronized?
Question is, how will it be synchronized? The propagation delay is different to different machines. So as part of this algorithm, each machine, you have to find the pairwise propagation delays, okay, and adjust for that. Okay, that is not shown here. Same thing you do in the Christian's algorithm. Okay, you will have to find the propagation delay between the master and this machine and master and that machine and adjust for it. Okay? So that part has to be done still. Any other questions? Yes, one question.
So if there is a application depends on the exact time, and some machine has to run the application because it's at the time, but after synchronization, maybe the time will be turned back. So is there any such problem?
Okay. Well, there's a question about application may depend on certain times. Here some clocks are being set backwards, some clocks are being set forward. Is there any problem? Okay. I didn't actually come to that, but when I talk about NTP, which is that's a protocol that is used commonly to do clock synchronization today, there is one important difference between whatever I've been talking about here and how NTP works, which is that time shall never go backwards. Okay, that's going to cause all sorts of problems. Okay, simply because you may have events that are designed to go off at a certain time. An event may have gone off, you roll the clock backwards and then you again go forward. Okay, running clock backwards causes all sorts of problems. Okay, so what you can only do is if your clock is faster, you can slow down the clock. Meaning you don't make it every 10 ticks, you may only tick 9 and you slow it down and have real time catch up with you rather than setting your clock backward. There is never a problem in setting a clock forward. So going from 250 to 305 is less of a problem than going from 325 back to 305. Because there may be now events that are already been timestamped that are in the future. You may have created a file which has a timestamp 320, which is now your time is 305. That's not even, the time hasn't even come by. Right? So you don't want that problem. So in real clock synchronization algorithm, you will not try to set any clock backward, but you will come to that. That is an important property. Okay? At the moment, we don't care. You're just simply saying you synchronize. Okay? If you're faster, you're pulled back. If you're slower, you're pulled forward. Okay? That's all you do. Okay. So that's basically the main idea. There are many other algorithms. So these are centralized approaches. There is a time server or a time daemon that's doing this. There may be decentralized approaches where You can basically think of Berkeley algorithm in a purely distributed, decentralized way, where every so often each machine broadcasts its time to all other machines, and all other machines do the same thing. So you collect time values from all other machines, you correct for propagation delay, you compute an average locally, and you set your average. This algorithm is simply computing the average of the clock values. Rather than collecting time from everyone, calculating the average and propagating it back, a decentralized approach would simply ask each machine to broadcast its clock to all other machines. Once you get clock values from all machines, you adjust for propagation delays and whatnot, find the average value, take the clocks and compute the average and set your clock. That would be a simple decentralized approach. No time server needed in that case. Okay. So that's essentially this approach. Okay. You will have resync intervals. Okay. As I was mentioning, the approach that is used today for most clock synchronization algorithms is called NTP. Okay. It's called Network Time Protocol. Okay. You can also use a Unix command called RDate to set the time, which is what it can do by just asking a time server. But most algorithmic machines are going to essentially use NTP. Okay. I'll talk about NTP in a later slide, but it is by far, it's a hierarchical algorithm. You can have a time server, and then you can have next level time servers and so on. And you essentially have to pick a time server to synchronize to. Okay. Just as your DNS server, most organizations will also run a time server. So you can go and synchronize your time with a time server on your local LAN. Okay. By default, if you look at most machines that you will get, Windows or Mac, they would have come with built-in a time server. Okay. So if you have actually looked at how your machine is synchronized, I'm going to show an example. So if you go into the time, so essentially you will say, see, so it's the thing checks exact date and time automatically, and it's giving your time server, which is time.apple.com. That is an NTP server that Apple runs for all of your machine. You can of course go and change it, or you can pick another time server, because they run three. They run one in Asia, one in Europe, and one here. You can go and just enter whatever you need. So if you put ntp.umass.edu here, you will now start synchronizing with the UMass NTP server. By default, it's synchronizing with a machine that they are running on behalf of all of their customers. Okay. So most of these machines will ship with some standard time server built in. You can go and change it. And that also tells you that by default, your machines are actually synchronizing themselves. This is why the clock doesn't seem to be as bad. If you stop this, if you uncheck this, you will see that slowly your machine will start drifting. But the clock synchronization will stop. Okay, so most of these will actually have this built into it. Okay. I'll come back to what NTP does, okay, in a later slide. But for now, you should just keep in mind that the accuracy of NTP is 1 to 50 milliseconds. That essentially says that if you run NTP, okay, what it means is your clock may be off by as much as 50 milliseconds with respect to real time. Okay. In general, that is pretty accurate, but if you have applications that need synchronization precision more than, that is more fine grained than 50 milliseconds, even NTP is not going to give you that. Okay, so if there are two events, or put another way, if you have two events that are maybe 20 milliseconds apart on two machines, you can't really tell what happened, because the error is greater than the difference between those two. If you have two events that are off by a second on two machines, you can reason about them, because if the inaccuracy is only 50 milliseconds, the one event has happened later than the other event based on the timestamp. But if the events are fairly close and closer than 50 milliseconds, you can't do it. This is a fundamental limitation of all clock synchronization algorithms. They will have some accuracy they can provide. If you have any two events that have happened within this space of one another that's smaller than that accuracy, you cannot say anything about it, because that is requiring a precision that is greater than what your synchronization algorithm will provide. Okay. So that's a limitation of a distributed system. Okay. This is also referred to the problem of not having a global clock. Okay. In a distributed system, a global clock is the same as a clock that you can use that is accurate and everyone can use that clock. There is no such concept. You're still using a set of local clocks that are being synchronized with one another to emulate one single clock in the whole system. Okay? But such a clock cannot be implemented perfectly ever. If you had a global clock, you could implement lots of problems, and distributed systems will be much more simplified. Okay? Typically, the way you are going to use time is you will have local clocks that are synchronized using time synchronization. There is going to be an inaccuracy as part of that process. Okay? So what that also means is there are only certain things you can do in terms of reasoning about time and time events and so on. Okay, is that clear? So we still have a little time, so I'm going to talk about another technique which will lead us to synchronization. This is the problem of global positioning system, or GPS. Okay? I presume you know what GPS is. Probably use GPS on phones or GPS receiver to get directions and so on. Okay? And as we will see, as part of running this GPS algorithm, you also have to have an inbuilt clock synchronization algorithm. So GPS actually has inbuilt clock synchronization, and you'll see why that is the case and how it works. Okay? So first, let's ask this question of what does GPS do? Okay, the GPS system was put in place for an arbitrary object to figure out its coordinates. Okay, so you basically, if you have an object and it says, where am I? Okay, with respect to, so if you need to find your coordinate, GPS allows you to figure that out. This is how you can go do direction and so on, because you know where you are. If you know where you need to go, you can figure out where to go next. Okay? So the problem of GPS is, given an arbitrary receiver which has an unknown coordinates x, y, z, it tries to figure out its coordinate. Okay, the way it is going to do is, you have basically what are called well-known beacons that are going to, that know their locations, and you have to figure out your location with respect to those coordinates. Okay, so the beacons in case of GPS are satellites. Okay, there are satellites in the sky that are parked at known locations in the sky, known x, y, z coordinates in the sky. Satellites know their location because you went and parked them somewhere. Okay? So they are going to broadcast their location. Like, I am a satellite, this is my location. They keep broadcasting this. Okay? And a typical GPS receiver can listen on to that broadcast, and it is supposed to figure out its coordinates x, y, z that are unknown with respect to that of a satellite. Okay? The question is, how do you go about doing that? And then we'll see what this has got to do with clock synchronization. Okay? Right now we are simply trying to do object locationing, trying to figure out the location of an object, but we'll see this has something to do with synchronization as well. Okay? So we'll start with a very simple example. Okay, let's say this pink dot is a satellite. Its coordinates are x1, y1, z1. Okay, known coordinates. x1, y1, z1 is known. Okay. Here's the receiver, which is a GPS receiver with the unknown coordinates x, y, z. Okay, coordinates are not known. Okay. Now this satellite is sending beacons saying, I am a satellite and my location is x, y, z. Okay. And these broadcasts are going at speed of light. Obviously, you're going to send a wireless signal, is going to propagate at the speed of light, and is going to hit anything that is trying to receive or tap into those broadcasts. Okay, so for sake of argument, let us assume that you receive these beacons at some later point in time after it's transmitted, and in particular, you receive them after time, or you receive them after time t. Okay? And for sake of argument, also assume that the distance between the satellite and this object is d. Okay. So now let's try to think. If you know these two facts, what can you tell about the position of an object? So if you are at a distance d from a known object, known coordinates, where would you be from that with respect to that object? Okay, so you have to be in a circle. Actually, you have to be in a sphere, but in 2 dimensions, let's say it's a circle. Okay, because these are the set of points. Okay, radius of the circle is d. These are all points that are equidistant as a distance d from the center. Okay? So if you could figure out I'm at a distance d from a satellite somehow, okay, you can, from an infinite set of locations, now you have sort of figured out you are on a sphere. Now, like 2 dimensions, you are on a circle here. Okay, let's just eliminate the z point. So if you are at a distance d, you are at, basically you could be on any of these points. Okay. The problem has not gotten better because these are still an infinite set of points. Okay, so now let's assume that there was second satellite, okay, whose coordinates are also known. Okay. And now you do the same thing and you figure that you are at a distance d prime from that object, or the object is at a distance d prime from the satellite, then you are going to be on another circle which is going to be of a radius d prime with respect to this. So I'm going to draw a second circle here. Okay, and this distance is d prime. Okay. Now, if you have 2 of these satellites, you have basically reduced your set of possibilities to exactly 2 points, which are the intersection of these 2 circles. Because you have to be on both of those circles. These are the only 2 points that are on both circles. Right? So if you have 2 satellites and somehow if you could figure out the distance, your distance to each of those satellites, then you can find your coordinates or have one of 2 possibilities for your coordinates. So you have basically gone from I don't know where I am to saying I am either here or I am here. Okay? Is that clear? If you have a third satellite, you can do the same thing. You draw yet another circle and essentially you have to be at the intersection of all 3 circles. So eventually you will narrow it down to a set of possibilities where you know definitely know where you are. Okay? So this is basically how GPS is going to work. Each GPS receiver, so there will be many satellites in the sky, okay, that are visible to you. Each satellite is going to have a known coordinates. Somehow you are going to figure out your distance to each of the satellite. That will put you on a sphere, because in 3 dimensions you are on a sphere, not on a circle. Right? So you will say, with respect to this satellite, I could be anywhere on this sphere. With respect to that satellite, I could be anywhere on that sphere, and yet another sphere. And I have to somehow find the intersection of those spheres, which will give you a set of points. Okay? Intersection of 2 spheres is not 2 points, it's a circle. If you have 2 spheres that intersect, you will actually have a circle. So if you have 2 satellites, you will be on a circle. If you have a third satellite, you will actually be on a set of points and so on. Okay? So you do intersection, and then you will say that some points will be high up in the sky. If you are actually driving on the road, you can eliminate those points. For example, you can say I'm on the ground, this other point is 100 meters in the sky, I don't think that is the right one. So you will basically use some heuristic and say this is my actual coordinate. This is how you are going to figure it out. Okay? I'm going to show you equations to do this, but this is the basic idea. And we still haven't figured out what this has to do with time synchronization. Okay, is that clear? Alright, so now let us go and do a little more details. So here is write us 2 equations to make this a little more formal. So here is our satellite. Coordinates x1, y1, z1. Okay. This is our GPS receiver. Unknown coordinates x, y, z. x1, y1, z1 is known, x, y, z is unknown. Okay. So our satellite is going to send broadcast. What is it going to say? It's essentially going to say, and we'll assume, furthermore we are assuming that the satellite is synchronized with an atomic clock, and we'll see why that is important in just a moment. Okay? So it will keep sending beacons saying, I am a satellite, this is my coordinates and it's currently time t. Okay, so it says this is the time. And this signal is going to propagate, okay, and it's going to hit this GPS receiver, let's say. Yeah. GPS receiver receives the signal at time t prime. Okay, which is its local clock. Okay, it has a clock. So it says I just gets a broadcast saying satellite coordinates x1, y1, z1, time t, you received it at time t prime. Okay. So now if you know these 2 facts, what can you do? you can try to first say what's the distance between these two satellites. That's the Euclidean distance between those 2 points. Okay? What's the Euclidean distance? Euclidean distance is square root of x1 minus x square y1 minus y square plus z1 minus z square. That's the Euclidean distance between any 2 points. Okay, simple geometry. Yes? Okay? X, Y, Z still unknown. I'm just writing some equations here. Okay? Now, if you are also told that a signal started from this satellite at time t, it reached this other point at time t prime, okay? And that signal propagated at the speed of light, what could you say about that distance d? Okay, speed, distance, time should tell you something. Right? So distance is also c times. Okay, that's the speed of light. Okay? Speed is distance over time. These two are the same distances. Okay, just 2 ways to compute it. Okay, so you're simply going to say c times t1 minus t is that. Okay. Except that we sort of forgot one thing, which is these 2 clocks are not synchronized with respect to one another. There is some error. Okay, an unknown error which is delta. That's a drift. That's also an unknown. We don't know. If they were perfectly synchronized, this would be the right thing. But they are not synchronized. There is some unknown drift between this time, this clock, and this clock. That is d. That's an unknown as well. Okay. So now we have how many unknowns in this equation? There are 4 unknowns. X is an unknown, Y is an unknown, Z is an unknown. This clock drift delta is also an unknown. Okay. So now this is basically one equation we wrote. It's a non-linear equation, but let's leave that aside for now. You can repeat this with another satellite. Okay. You'll get essentially the same thing. Okay. Delta is going to be the same because these 2 satellites are now synchronized with an atomic clock. The drift of this receiver with that satellite is same as the drift of this receiver with this satellite, because we are making a simplifying assumption that these 2 satellites are extremely well synchronized with an atomic clock. They may carry an atomic clock, let's say. Okay. So you can write another equation here, which is c times t2 minus t, okay, minus delta is x2 minus x square plus y2 minus y square. Okay. Same 4 unknowns with second equation. So you keep repeating this. You will at least need 4 equations for 4 unknowns. Okay. But these are non-linear equations, so you can't actually solve a non-linear equations with just 4 unknowns. So if you have at least 4 satellites, you can try to get this. But as you have 5, 6, 7 satellites, you will get a bunch of these equations. So you have a set of these equations, and you still have 4 unknowns. You solve them, okay, with whatever solver you want, and eventually you will basically find the answer to x, y, z and delta. Okay? Because you need to estimate delta for all this to work. Okay? You are solving a clock synchronization problem as part of a positioning problem. Is that clear? Otherwise you wouldn't know how to estimate this value. The 2 clocks are off. You can't say it started at noon, I received it at 12:01, so that is 1 minute has elapsed. That is meaningless if my clocks are not synchronized. So I need to synchronize my clock at the GPS receiver for me to figure out the position of the GPS receiver. So every GPS positioning problem is also solving a clock synchronization problem. Okay, is that clear? So you could actually simply attach a GPS receiver to your computer and ask it for the time, and your time is actually going to be the same as the time of the satellite if it's synchronized well. Alright, so this is basically how you do GPS. You will at least, there are 4 unknowns. This is the same set of equations. The 4 unknowns, you need at least 4 satellites, but these are non-linear equations, so typically you need more than 4. Okay, the better your sky, the more satellites you can see, the better your positioning is going to be. Typically by 6 or 7, you see 6 or 7 satellites, your GPS is latched on. It sort of knows where you are, because it can solve those equations and get precise values. Remember, when you're non-linear equations, you're going to get multiple solutions. That's the same problem as here. This is why there are two solutions to the problem of variable. Okay, because these are non-linear, same non-linear equations in 2D. Okay, it's not giving you a unique solution. So you have to use heuristics to eliminate. If this is closer to the ground and this is 100 meters up in the sky, your GPS receiver will eliminate that solution and say that's where I am. So beyond some point, you need some heuristics like that to figure out which is the right answer to variable. But delta you have to figure out nevertheless. Any questions on this? Okay, so we looked at several different clock synchronization algorithms. We looked at GPS, we looked at Berkeley algorithm, we looked at Christian's algorithm. I showed you briefly what NTP does. Okay, it is essentially a version of Christian's algorithm with better ways to estimate and as a hierarchy, just to eliminate the load on the time server. There are master time servers and there are what are called strata, which are hierarchical time servers. They are synchronized with the master and then machine synchronized with them and so on. Okay? But same idea, there is not a whole lot different that's going on. Okay? So all this is telling you now, if you synchronize your clocks, okay, you will be within the error of whatever the clock synchronization does for you. This is also why even in GPS, the error comes from the error in clock synchronization. GPS can pinpoint you to within a 10 to 20 meter radius. That is because it doesn't know exactly how to synchronize the clock. Otherwise, you would get one coordinate, not a set of coordinates. Okay, so the more better the clock synchronization, the better the positioning as well. Same issue. So what I should tell you is, for many applications, if you run a clock synchronization, all the clocks are actually synchronized with respect to one another, plus minus the inaccuracy of the synchronization algorithm. You can use those clocks to reason about time. You can take the timestamp of one machine, timestamp of an event on another machine, compare them. You can run your make. Okay, that example I showed you. Okay, the clocks will be synchronized unless you actually hit save on your source code within 50 milliseconds of whenever the previous make ran. You should be good. Okay, if you say made changes to your file after you compiled, okay, and if it was 2 minutes later, you should not have the problem that we started off with anymore. You will not have the build server running much faster than other machines, and then you can't tell what time it is and whether the source code file is newer than the object file. All these problems should go away. Okay? But you will never get full precisions. Whenever there are two events, okay, you are essentially going to have this problem of figuring out if they are very close to one another, what order they happen. You cannot tell, okay, because there is an inaccuracy in the synchronization. Okay. So there are many such clock synchronization algorithms. I'm not going to go through the variants. There are some that are used in wireless networks that look at propagation delays of wireless networks, which are slightly different from how you do this in the wired world and so on. So this is actually an area of research. If you go and read or look for papers on synchronization, you will see hundreds and hundreds of papers that are all looking at various facets or trying to solve the problem in a slightly more efficient way for a very specific scenario and so on and so forth. Okay? But the straightforward approach is you just use a clock synchronization algorithm such as the one I was showing you, like NTP. Yeah, that's a very standard way to do things. So very quickly, here is NTP as an example. Okay? Same thing as Christian's algorithm. You ask for time, time comes back, you have to find those estimates. Okay? And you use 8 pairs of measurements in NTP, not just one. Okay? So you can get a better estimate. Okay? That's the first thing. So you try to make these estimates more careful. The second more important problem, as I said, is if your clock turns out to be faster than the time server, you don't set your clock backwards. You do not repeat time. You cannot have time events that have already happened that are in the future. Okay? So in NTP, clock cannot go backwards. What that means is if you are actually faster than real time, you have to artificially slow down the clock in your machine. Okay? What that says is if the crystal oscillates n times, that would normally be 1 second. Every so often you will basically skip the second and slow things down and have real time catch up with. Rather than moving the thing backwards, you artificially slow it down. You don't tick at the same rate. Even though the clock is ticking, you hold it back from ticking forward. Okay, this will slow things down until time catches up. That is one thing NTP does which is actually good. Otherwise you will see all sorts of problems wouldn't encounter. Okay, so that's essentially the variant of, and as I said, it's hierarchical, which means there are a set of these servers that you can set up in a tree. Each server synchronizes with its parent. Okay, and you can synchronize with any machine in that, any time server machine in that hierarchy. Okay, similar to DNS, where you had a distributed set of naming servers, a distributed set of time servers as well. So I'm going to quickly introduce in the next 2 minutes this notion of logical clocks. Okay, and then we'll actually talk about what to do with logical clocks next time. So first problem that logical clocks try to address is that clock synchronization or synchronization of physical clocks is never going to be perfect. Okay? By and large, for most scenarios, or when you try to look at events, you can figure out what happened and what order they happened in, but sometimes then you will not be able to figure this out. So what can you do about this? So here what logical clocks do is they give you a notion or an abstraction to reason about ordering of events without using physical clocks at all. You will get rid of physical clocks altogether. Okay? You will use this notion of a logical clock, which doesn't actually have anything to do with real time, to figure out what order things have happened. Okay? So this will get rid of the need to have clock synchronization at all, because you are no longer depending on real clock timestamps to figure out order in which things are happening. Okay? So the question is, how do we go about doing that? So we will have some ideas on how to do it. So the main thing what we want to actually arrive at is we need processes to agree on the order in which certain things have happened rather than the time at which they occurred. In some cases, you may actually be dependent on time. If you say, what time did this person log in last and so on, that's dependent on actual time. But in many cases, you're using timestamps as a proxy to figure out, is this event happened before this. In Make, you're simply saying which file is newer. Is the source code newer or the object file newer? Okay. So you just want to know, did you modify the code since the machine compiled the code last? You don't care about, was the code modified 10 minutes later, 15 minutes later, that's not important. You just want to reason about the ordering of events. So if you only want to care about the order of event, not of the time of events, can we simplify this whole process altogether and not depend on physical clocks at all, which are fundamentally going to be inaccurate? Okay, they are going to depend on a synchronization protocol with some inaccuracies. Okay, so what we will do is we will define this abstraction called a logical clock that will simply allow us to reason about order. If you ask what time this event happened, you cannot say anything because that's not a real clock. But if you say, here's event A, here is event B, can you look at this and tell me what order they happened? We'll be able to figure that out. Okay? And for most applications, that is what is more important rather than the time. So we are going to do this next time, not today, because we ran out of time. So we will actually have this whole class of algorithms that will allow us to think about timing of events, but ordering of events. So that's what is coming next. Let's stop here for today. Okay, so we'll continue on next time.